All right, so the special system that we're going to deal with, because it gives us nice, easy, clean results, is an ideal gas. And so if we think about the four sort of special processes that we talked about with an ideal gas, so here we're going to start in state A. We've got a PV diagram, so pressure on my vertical axis, volume on my horizontal axis. And the fact that I can draw out each process tells me that I have a reversible process. So my reversible process to state 1 means that I start here at state A, head out to state 1. I'm obviously doing that at a constant pressure because I'm moving along a horizontal line. So this is an isobaric or constant pressure process. And again, what's nice about an isobaric process is the work done by the gas is easy to calculate. It's simply the area under the PV curve. So the work done by the gas would be positive as it expands and would be given by a rectangle that has this height, whatever the pressure value is, and this delta V, so whatever the volume of the expansion is. Again, if it's so that's in going from state A to state 1. Obviously, if we went in the other direction from state 1 to state A, then we'd end up with a negative work done by the gas because you would have to do positive work on the gas to get it to compress. So in that case, again, our V final minus V initial, well, you'd be at a final volume that's much smaller than your initial volume because volume's increasing to the right. And so you'd have a negative if you went from negative work done by the gas if you went from 1 to A, positive work done by the gas going from A to 1, and in both cases that calculation is just pressure times delta V. From what if we start in state A and go to state 4? So again, what's staying constant here is the volume. So again, the 1 constant pressure and 4 constant volume, those are easy to read on a pressure volume curve because it's easy to see that you're keeping either the horizontal or vertical variable constant here. And so again, we said that we know that if we have a isochoric or constant volume process, then the area under the curve is 0. So the work done by the gas is 0. Again, if you don't change volume, then the work done by the gas is 0. If we start in state A and go to state 2, so again, here's a situation where we actually have a constant temperature process. So going from A to 2 is isothermal. In an ideal gas, the internal energy only depends on the temperature. So part of why isothermal processes are really important with ideal gases is because an isothermal process means not only does the temperature not change, but neither does the internal energy. So we've talked about sort of special processes for which each term in the ideal gas law becomes 0, and for an isothermal process with an ideal gas, the change in the internal energy of the system becomes 0. So this is one where you're left with, as you go from state A to state 2, you're going to take in energy as heat, and all that energy is immediately going to go into doing work as the gas expands. So you're not changing the internal energy at all because the temperature is going to remain the same. And that's what the temperature is measuring in an ideal gas, is the temperature is measuring the internal energy. So what do isotherms look like on a PV diagram for an ideal gas? And so the easiest way to think about this is, well, here's our ideal gas law. And so in an R, well, if we're not changing the amount of stuff we have, and R is just the gas constant, and T is constant itself along an isotherm, then this nRT term, all these things are constant, which tells us that the pressure is inversely proportional to the volume. So as you increase the volume, you've got to drop the pressure at just the right way so that the product of P times V always stays the same. When you do this, you get basically these inversely proportional curves. So this should look like a 1 over x curve. This is just a 1 over x curve for sort of meaningfully reasonable pressures and temperatures that we'll deal with an ideal gas. And so one of the things to recognize here is, so these are all isotherms, and they're all at different temperatures. And you can see from the labeling here that this blue curve is the hottest of these isotherms. The yellow curve down here at the bottom is the coldest of the isotherms. So that tells us that the temperature increases as you move up and to the right. So if we started at some point and went straight up, the temperature would increase. If we started at that same point and moved directly to the right, we would still see our temperature increase because we're moving to higher and higher isotherms. So moving up and to the right on a PV diagram increases the temperature when you've got an ideal gas. Moving down and to the left will decrease the temperature. So how much work is done by an ideal gas during an isothermal process? And again, this is fairly easy to calculate. We can start with our definition for the work done by the system, and it's just the integral from some initial to final volume of P times our little differential volume steps. And since we know that for an ideal gas that we can write the pressure as nRT over V, we go plug that in. Again, nR and T for an isothermal process, these things are all constant, assuming that we're not changing the amount of gas that we have. And so nRT gets pulled out, and we're left with the integral of dV over V, which we know is just the natural log. It gets evaluated at the endpoints. And so here's the expression for the work done by the gas. So the work done by the gas along an isotherm, again, this is only applicable along an isotherm, is nRT times the natural log of the final volume over the initial volume. Now, given what we know about natural logs, if the final volume is larger than the initial volume, meaning that the gas expands, then this ratio will be larger than 1, and the natural log of anything larger than 1 is positive. If, on the other hand, your gas compresses so that the final volume is less than the initial volume, then the ratio inside the natural log term will be less than 1, and the natural log of a number less than 1 is negative. So we get the signs that we know we should get, right? We get a positive work done by the gas during an expansion, a negative work done by the gas for a compression from our expression. So the last special process we've got is if we start at state A and proceed to state 3. And this is our adiabatic process. So again, this is the process where no energy is being transferred into or out of the gas's heat. So here we have, going from A to 3, we have an adiabatic expansion. If we went from 3 to A, we would have an adiabatic compression. The key thing to note is that an adiabatic expansion falls off more steeply than an isothermal expansion. So here's my isotherm, that's 2. Here's my adiabat going to 3. So the adiabatic expansion falls off more quickly than the isothermal expansion, which means since I went from starting on this blue isotherm and I've come down, I have to have moved to a cooler isotherm. So my adiabatic expansion moves me to a cooler isotherm. Now, if you remember when we talked about adiabatic expansions originally, we said that with an adiabatic expansion, because Q equals 0, if you expand, if your system expands, then the internal energy of the system has to decrease. And because for an ideal gas, the internal energy of the system is directly related to the temperature, that's why the temperature also has to decrease. So this is just sort of the picture that goes along with that idea that for an adiabatic expansion with an ideal gas, because the internal energy decreases, then so must the temperature. So how do we know that an adiabat is going to be steeper than an isotherm? Well, we said for an isothermal expansion that pressure times volume, that has to remain constant. For an adiabatic expansion, we have a different rule, and it tells us that pressure times volume to the gamma has to be constant. And gamma takes a different value for different types of ideal gases. For a monatomic ideal gas, gamma is 5/3. For a diatomic ideal gas, gamma is 7/5. After that, once you go to sort of more complicated ideal gases, it depends on the particular structure of the ideal gas. But for monatomic and diatomic, we're basically going to be able to use these two simple values. And so what you notice is both of those values are larger than 1. That's the important thing here. So when you think about what's going on, well, if I know that PV to the gamma has to be constant along my adiabat, then that means at point A, which is on the adiabat, so the pressure at A times the volume at A to the gamma, has got to be equal to, since point 3 is also along the adiabat, the pressure at 3 times the volume at 3 to the gamma. And I can rearrange this, and what I get is the pressure at 3, which I know has decreased, is going to be equal to the pressure at A, and instead of this just being PA times VA over V3, as it would if this were an isotherm, I get that the pressure at A, or the pressure at point 3 is going to be the pressure at point A times the volume at A divided by the volume at point 3 to the gamma. And this is clearly less than 1 because I have expanded in moving to point 3. So my ratio here is less than 1, and then I'm going to take it to a power that is greater than 1, which means this will be even smaller. So the easiest way to think about that, again, we don't deal with 5/3 powers or 7/5 powers all that often, but you guys do know that let's say I doubled the volume in my expansion, and if gamma were 2, just to make everything easy, well, you know that instead of this being 1/2, once I squared it, it would be 1/4. So when you take something less than 1 and you raise it to an exponent that's greater than 1, you make it smaller still, which is why the pressure at point 3 has to be less than the pressure at point 2. It's how you know that the adiabat falls off more steeply than the isotherm. And so these are the these are the rules that we'll play with for our special processes with an ideal gas. And so what this will let us do is it will let us actually solve a lot of thermodynamic problems using ideal gases. And so that's what we'll spend a good portion of next week doing.